The samples go inside of this chamber. The chamber is, the chamber is under vacuum. So all the samples will be under vacuum. They'll have to be vacuum compatible. Because they're being bombarded by an electron beam, they also have to be conductive. So there is some sample preparation that we have to do. Basically, the samples get hit by an electron beam. The electron beam hits the atoms on the samples. The atoms, when they get excited by the electron beam, they eject secondary electrons, and those secondary electrons are detected on the SE detector, and it generates an image like the one you saw a few minutes ago. The electron generator, it's either field emitter or a thermionic source. Our instrument has a field emitter that makes it a better tool in terms of being able to produce a higher resolution. The electrons go down a column. This is the column right here. And 1 second here. They go down the column. They get focused by different lenses. It goes through an aperture. It goes to another set of lenses. And they finally go to the bottom of the chamber where they hit the sample, rasters the beam, and you can see an image gets generated on your screen. So we're going to see that real life today. What generates the image are the secondary electrons that you see on the surface here on green. They get expelled from the sample and they get detected by the SE detector, and you get topographic information of the surface of the sample. We have several detectors in our machine. One of them is an SE detector, secondary Everhand foreign detector. It's the one that you see here. This is what we use to do typographical images. And we also have a backscattered detector that gives us contrast based on the atomic weight of the element. So if you have a heavy element like iron or lead, and you also have a lighter element like aluminum, the lead or the iron is going to look much brighter than the aluminum using the BSC, backscatter detector. The backscatter detector, backscatter electrons are basically the same electrons that are coming down from the column. They have an elastic collision with the atoms and they bounce back into the detector. So for that purpose, since it bounced back up again, the detector has to be positioned on the top of the sample like you saw there in the last video. So let's go now to our piece of equipment here. And right now you're seeing the chamber inside.
Hey,
so yes?
Can you please dismiss the reminder that's in your bottom right? We can see
Very
that.
bothering.
The reminder on the bottom right.
There's a reminder on your window for the corrected TEM demo. Somewhere on one of your screens. Yes, dismiss that. Thank you.
Sorry. Thank you. Yep. Okay, so what you're seeing here is the vacuum chamber. This is under vacuum, just like being in space, right? So there's no air inside of the chamber. Electrons don't like to be in air because they get all scattered out. So in order to get an electron beam down this column nice and focused, it has to be under vacuum. Here we can see the SE detector. On the left-hand side, this is our EDS detector, which we're going to use for doing a little bit of CSI work and a meta-analysis. And on the back, we cannot see it right now. It's a backscatter electron detector. So I will show that in a minute. Okay, so in the middle here, we have our SC, or our window where we're going to get the image. We're just going to go ahead and turn the beam on. And what we're going to be looking at first, one more thing, this instrument can do, the beam voltages can go anywhere from 1 or 2 kilovolts all the way to 30 kilovolts. Today for imaging, we're going to be running at 5 kilovolts because we're going to be looking at some fragile samples. What we have here, it's a set of bugs in a human hair. So one of the things I'm going to try to do today, since it's Nano Day, I want you to get an idea of what a nanometer looks like or what a nanometer is like. It's really hard to kind of see a nanometer with the naked eye. So that's why we have these fancy tools to kind of be able to see down to a nanometer level. We're not going to quite be able to see 1 nanometer with this machine. I'm going to leave that to Nick on our next presentation for the TEM. But here, we're going to see features that are roughly 10 or 20 nanometers in size. Okay, so our first stub right here, we have it full of bugs, and I just want you to get an idea what the size of this stub is and the sizes that we're going to be dealing with in a minute. So if you put a marker in there, this stub is about 13 millimeters in size. So if you took a ruler that you use at school, you should be able to see 13 millimeters with the naked eye. Okay, so let's go ahead and start zooming in to our sample. And the next thing I want you to see, it's a human hair. So if you pull a little piece of hair out of your head, and we put it on SEM, this is what it looks like. With the naked eye, it's just a little tiny filament. But if we put it under the SEM, this is what a piece of hair looks like, a human hair. So is it a nanometer in size? No, it's actually quite bigger. So if we take our measurement tools again, and we measure the diameter of a human hair, we can see that it's roughly 73 microns. Okay, so just remember, in 1 millimeter, there are 1,000 microns. So we saw that the stub was 13 millimeters. So in 1 millimeter, there are 1,000 microns. Okay, so our hair is 73 microns. So just remember that number. Let's zoom out a little bit, and let's go now to, I had a mosquito in here. So this part, this little organ probably fell off of the mosquito, and it looks pretty cool. It looks like a plant, right? This look like leaves, like a palm tree. So let's go ahead and zoom in. So now we are at 4000x magnification. So you can see the magnifications on the bottom of the screen over here in the bottom left. Just keep in mind that an optical microscope that we use for optical imaging, the highest you can do a magnification is about 200x. And right now we are 4000x, so much higher. All right, so let's zoom in a little more and see our little features here. And let's see the size of these little leaves. This is an organ for a mosquito. I'm not sure exactly what it is, but it just looks pretty nice. So if we put our measurements in here, these leaves are about 6 microns. So we're getting quite smaller now. We went from 70 microns of a human hair down to 6 microns, right? Okay, so let's now drive to a different location on our stub. So let's see if we can find a mosquito around here. Wow, look at that. Look at those circles, right? So if we zoom out, so since we all live in Florida, we know Florida is infested with mosquitoes, and every time we kill a mosquito, this is what you're hitting with your hands. I don't know if you should feel bad about it or not, but this is what a mosquito looks like under an SEM. Unfortunately, this little guy took a lot of beating when I was putting it on the sample, and a lot of his parts came off. Like it was already pretty dry. So what we're looking at here are the eyes of the mosquitoes, and it's got hundreds of eyes, right? And that's why they tend to fly away before you hit them with your hand, because they can see really, it seems like they can see really well with all these eyes. So if we zoom in here, let's see how big the eyes of the mosquitoes are. All right, so if we put our measuring tool, so the eye of the mosquito is about 20 microns, so it's a little bit bigger than those feathers that we saw there earlier. All right, so let's move over now to the mosquito. Let's adjust our contrast and brightness of the tool. So this is part of the body of the mosquito. You can see that it's filled up with a bunch of little hairs. And what we're gonna do here is we're gonna correct our focus. We're gonna focus our beam so it looks better. So you can see the body of the mosquito just full of a bunch of little hairs. And if we keep zooming in, so right now our magnification is up to about 10,000x, right? See little spikes. And if we use our measuring tools, let's see here. One of these little hairs of the mosquito body, it's about 280 nanometers, so 0.2 microns. So remember, in 1 micron, there are 1,000 nanometers. So these are 280 nanometers. So now we're getting into a nanometer world in the mosquito body. So you can see that nature creates nanometer size features in here, and they're very good looking. So it's like a nanoforest, what we're seeing here in the mosquito body. Okay, so let's move over to, I think we also have a tiny ladybug. So in here, this was a tiny ladybug that I found dried out on one of our windows at the lab. And there's a lot of charging going on here. So a lot of the samples were coated with gold palladium because they're not conductive. So that's why you see the image being a little bit brighter over here, because that layer of gold palladium wasn't continuous. So the electrons are hitting that surface and then have nowhere to go, and they're charging up the sample. Adjust our contrast and brightness real quick. So if we zoom in into our ladybug, this is like an area underneath the wing. And you can see that there's scales, right? Those scales that look like fish scales almost. So this is underneath the wing of a ladybug. And if we look at the size of the scales, I don't know, let's just measure from here to here. They're 4 microns. So they're 4,000 nanometers, 4.4 microns. Okay, so let's zoom out here and let's see if we can find the eye of the ladybug. So here's the eye of the ladybug, and I'm gonna go ahead and increase the contrast and brightness a little bit. It looks out of focus. I'm gonna refocus the beam. Okay. So you can see there's the eye of the ladybug. It looks kind of similar to the mosquito eye, but now the little domes here are kind of closer together, and look at all these tiny little hairs sticking out of each eye, or out of the sides of the eyes. And if you see the size of these are roughly 1 micron, so about 1,000 nanometers, so a little bit bigger. Okay, so let's zoom out now. And so now that we've seen a couple samples of the natural world, or bugs, or like nanometer features in bugs, let's go find out what can we make here at our facility. So let's look at a sample that we actually manufactured here using our A-beam lithography tool, which also uses an SEM to build things. So SEMs are pretty diverse. You can use them for imaging small samples, so you can also use them for creating devices, computer chips and things like that. All right, so okay, so this is a flat silicone chip, and it has a layer on the surface of E-beam resist. And what we did, just like you do printing, we raster an electron beam using an SEM over the surface of this sample. and we were able to expose the e-beam resist and create shapes, right? So we drew all these shapes first on a computer, the SignCAD software, and then we put the sample inside, and the electron beam went over all these features and was able to write all this. Of course, the film that is on top of this, it's a e-beam sensitive film. So when it gets exposed to the electron beam and you put it on a developer, the area that gets exposed with the electron beam actually dissolves, and you end up with this channels in here. So this is kind of like a little flower looking thing. And what we're gonna do is that we're gonna see how small we can build things around here at the lab. So this is something that we work with all the time. Our researchers use this tool to advance our research. All right, so in this flower, let's zoom in into this little corner over here. And let's try to get a better image. Okay, and let's use our measuring tools and see how big these gaps are. So if we put a bar here and a bar here, so that's 90 nanometers. So we're getting pretty small now. So this is almost the size of those hairs that we saw earlier in the mosquitoes. So we can make things here that are 90 nanometers in size. Let's see, put another bar here, that's 71 nanometers. Now, not quite 1 nanometer yet. It's pretty hard to make something 1 nanometer in size. But this is what 70 nanometers kind of looks like in the SEM. One thing to look at before, take a note of is notice the magnification on the bottom of the screen is 50,000x. So we have magnified this image 50,000 times to be able to see it. All right, so let's zoom out and drive to another area over here so we can see other nanometer size patterns, perhaps these little squares. Okay, so we have an array of squares here. We use this pattern to test the machine and see how well it's writing. So now our magnification is close. Let's do 100,000x. So we have 100,000x magnification. And if we throw measurement bars in here, we can see that these tiny little squares are 100 nanometers. Then the gaps in between these lines are roughly 55 nanometers, so that they're quite small. All right, so I do have a lot of stuff to show you. So let's move over to something else. All right, let me zoom out and let's go over to an LED. So we were able to find a commercial LED that you have in your cell phones. We were able to strip it open and put it on the tool. So let me drive over to the LED. So with the LED, what we're gonna do, it's we're gonna switch over to our EDS detector, which is this screen over here. And we're gonna use this EDS detector to figure out what the LED is made out of, right? So what we're gonna do, so for that, to be able to do elemental analysis on this LED, we need to change our voltage real quick. So what I'm gonna do here is I'm gonna change the voltage of the machine to, I'm gonna go from 5 kilovolts to 15 kilovolts. So that's gonna take a little bit of time. And I'm also gonna insert our backscattered detector. So look on the left window on the screen, and you're gonna see a detector being inserted on the bottom of the column on your black and white screen where you can see the samples. All right, so we inserted a backscatter detector. So it's this guy over here. And I need to beam intensity, get that 16. Change that. And we do a little bit of adjustment. Okay, so now we see our LED again. We see a backscatter detector in the bottom. So right now we're using the secondary electron detector. We're seeing a lot of topography. So we can see the traces of LED. You can see this part is a little bit higher than the bottom. A lot of the contrast is based in topography. So you can see here the cables that are connected to the LED. And we want to know what these things are made out of, right? We want to know what these cables are made out of, what these materials are made out of, what the bottom over here. So let's switch over to a backscatter detector and let's see, remember when we see a backscatter image, the heavier elements will show up brighter than the lighter elements. So we switch to the backscatter image and we notice that these traces of metal, they're super bright. Also these here, and this chunk over here almost disappears. So it's very, very light. So let me switch back to the SE. So you can now see the bottom. Oh, I hit the wrong key, sorry. There we go, shut off the beam by accident. So back to the BSE, see this bright line. So let's try to figure out what they're made out of. So let's switch over to our EDS detector, which you see here. And what we're gonna do is we're gonna take spectrum of the sample that we're looking at. So let me do a few adjustments in here. We'll get that running. So let's get our image on this computer real quick. Okay. All right, so here's the LED, and we want to take spectrum of this whole thing and see what elements are in there. 1 second. Let's launch this again because we're getting some false data in here. All right, so this is a spectrum for the LED, and we can see that it's mostly made out of gallium, there's silicon, and this is probably gold. There's some oxygen. So there's all these elements inside of the LED, or that the LED is made out of. So the other things that we can do with this EDS software is we can also create an elemental map of the LEDs. So let me show you a quick example of this elemental map. So I ran this a little bit earlier today because it takes several hours to be able to get these maps to work. So this is the picture of the LED we were just looking a minute ago. And we noticed earlier that on our EDS map, on their EDS spectrum, that it had silver, it had gold, it had silicon, it had gallium. So let's see what these things are made out of, right? So if we switch to our silver map, you can see that the traces, the cables for that the gold wires are connected are mostly have some silver in them. If we switch to our gold map, we can see that all these traces are made out of gold. Okay, so this is an X-ray EDS map of the LED. If we look at a silicon map, you see all this stuff is made out of silicon. Aluminum, remember the bottom part? Aluminum is a lighter element. On our BSC detector, the aluminum looked pretty dark. That's because the bottom part of the LED is made out of aluminum. So you see a lot of aluminum in the bottom here. And then we also saw a lot of gallium in our spectrum. So if you look at the gallium map, you can see that there's a lot of gallium, which is the LED is mostly made out of. And then we can put all these maps together and we can have a composite picture of the whole LED. Different elements. So you can see on the left-hand side here, you can see the gallium. It's the green part, and then the gold is kind of these traces over here, and there's some silicon in there, and so on and so forth. So this is a great tool to see what things are made out of in the SEM. All right, the other thing I wanted to show you real quick, we only got 1 more minute left. It's a meteorite. So one of our researchers here, Christy, since a lot of her work she used to do a lot of meteorite work. She was kind enough to get us a meteorite. So we can figure out with our instrument, with our EDS detector, what a meteorite is made out of. So here is our meteorite. Let me switch over to the other screen. Focus on that. And let me switch back to the SE image. Okay, so this is the surface of a meteorite. You can see there's a lot of topography in here. And if we want to, and this is using our SE detector, secondary electron detector, where we can see a lot of topography of the meteorite. If we want to see, what the meteorite is made out of, we can switch over to a backscattered image, and we can see that there's a lot of bright features in here. So remember earlier we said the heavier elements show up brighter than the lighter elements. So I can deduct that this is a heavy element over here and these are lighter elements. So if we switch over to our EDS detector screen, I did a map of this area earlier, and we can see that a lot of the meteorite is made out of iron. So there's a lot of iron in there. It's all the blue parts over here, which was the brightest part on the EBSD detector, right, that we saw earlier. So that big thing is, big area there is mostly iron. And then the lighter area is made mostly out of silicon. And then you also have a lot of magnesium in there. You have a lot of oxygen. There is some carbon. I think that's carbon contamination just from being in Earth. And this is the overlay image of all the elements. If we look, this is the EDS spectrum for that surface. You can see there's a lot of silicon, magnesium, and oxygen, and iron. And so it's a very useful tool for doing investigative work to figure out what things are made of, okay? All right, I think we still got a few more minutes. Let's drive around this meteorite and see what else we can see here. If we zoom out on this whole piece, you can see that there's a lot of iron. Oh, sorry. If we zoom out on the whole piece, you can see that there's a lot of iron in the meteorite. So all these bright spots that you see on the SEM image are mostly made out of iron. Again, I'm using the backscatter signal for this. Heavier elements are brighter. If I switch over to the SE signal, they kind of go away. And at this point, we can just see mostly topography. So let's zoom in a little more. There you go. So this is what a meteorite looks like when it lands in Earth. So a few other samples on an X-ray computer. Silicon gold. Let's see here. So here was another sample that we did earlier. These are kind of traces, silicon and aluminum. So these are aluminum wires, and this is silicon. And if we go to an overlay map, you can see the aluminum wires in here. This is using our ADS detector. This is a silicon map. And then if we overlay these two together, you can see the aluminum and the silicon together. Let's do this again. There we go. So you can see aluminum and silicon. So very useful tool for researchers here at the RSCs. Okay, Kaylan, are we out of time now?
Yes, Andres, I think the next one is starting.
Okay, so check on the chat and make sure you guys make a note of the next event. The next event is going to be the aberration corrected TM, and it's going to start pretty soon. And Nick Rudowski, and it's going to be the host, and I believe John from FEI or Thermo Fisher is going to be driving the instrument and doing the demo. Thanks for your participation, and we'll take a note of any questions that you guys had, and we'll answer them via email later on. Thanks for coming.